Welcome to today's webinar. The topic today is load transfer options in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Niklas Wanke will be the presenter. He works in our customer support team and he's also responsible for the add-on steel design and for the development of the new RFEM 6 add-on for the design of towers and masts. Okay, I show you how you can ask questions. At first, I switch off my camera that you can see the full screen. At least, yeah, for the attendees who participate the first time. Just press that button with the question mark, then you can enter the question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Niklas. Niklas, it's your turn.
Thank you, Andreas, for the introduction, and welcome from my side as well. Before we start, I want to show you the content for today's webinar. And I prepared 4 points at all. Of course, we will have a look at the different possibilities of load transfer in RFEM 6. First of all, we have the feature load transfer surfaces, and this will also be the main part of the webinar. But I also want to show you the 2 load wizards, which have the possibility of load transfer. And this is the load wizard member loads from area load and member loads from free line load. Last but not least, I would like to give you a small little outlook for planned features in comparison with the load transfer function. Okay, with that, we can start with the first point, load transfer surfaces. Before we switch to RFEM 6, I have prepared one little page because I would like to give a small overview about the basic principle of load transfer and what is meant with that. So normally, or in many cases, you will have the case that you model a construction, like for example, the steel hull, and you want to model it as a framework in many cases, because it could be possible that you don't know many things about the walls. So maybe you don't know how thick and which materials the walls should have. Maybe you don't know the exact stiffness of the walls. So in many cases, you will model it just as a framework. Nevertheless, you always or mostly have surface loads on this framework. For example, from wind or also snow loads on the roof. And then there's the question, how can you model these surface loads? Because normally you would like to apply the loads on the framework, on the members. And therefore, we have this feature of the load transferation, which should make it a lot easier for you to apply the loads correct without thinking too much about how much load every member will receive, because this will happen automatically. Another advantage of the load transfer surface is that you don't have to consider the stiffness of the surface. So the surface can consider loads, and it can transfer it to the connected members or other objects, but it does not have any stiffness at all. So you don't stiffen your whole system with these surfaces. And in many cases, that's exactly what you need, because if you don't know the exact stiffness or don't want to consider the stiffness of the surface for your structural analysis, then this would be the perfect feature. the load transfer surface. Okay, now we can switch to the program, RFEM6. And to show you all possibilities of load transfer, I have prepared such a really small and simple model of a small steel hall. We can also have a look at the dimensions really shortly. So I will show you. It's a really small hall with 4 meters times 5 meters. Maybe you can park your cars under it or something like that. And the hall has a height of 2 meters. And the roofs have a little pitch. So the height difference is 17.5 meters between the middle and the rim of the hall. As you can see, I already created one surface of the one half of the roof, and this is already a load transfer surface. For the second half of the roof, we will model this surface together so that you can have a look at the process of modeling it. For that, I will choose the option New Surface with the option Select Boundary. Now we are in the surface dialog, and first of all, we have to select our stiffness type. So this is where the magic happens, because here you can select the load transfer surface, and that's exactly what we want for this webinar. An alternative would be to select another stiffness type, for example, standard stiffness. And then you can create your thickness and your material. And in this case, it would be possible to activate this option, Activate Load Transfer. In this case, you can consider the stiffness of the surface, but also do the load transferation. But for this example, I would like to choose the load transfer stiffness type, which means that we don't apply any stiffness to the load transfer surfaces, just do the load transfer. As you can see, this option is, in this case, automatically activated. Okay, by choosing the load transfer stiffness, we get an additional tab. And this is where we can make all our settings for the load transferation. First of all, we want to have a look at the categories area. And first setting is really important. This is the load transfer direction. And basically, we offer two different methods of load transfer for the surfaces. The first method is called isotropic FEA, and the other method is called the stripes method. So these two methods work completely different, and we will have a look at both. But first of all, let us select the isotropic FEA method. I want to give you a small explanation about how this method works. And for that, we can have a look at this picture at the bottom right of the dialog. Because in this picture, it's tried to explain how this method works. So this first picture is what you see in the main model. So you have your load transfer surfaces, you have probably a connected member or other connected objects, and you have your applied load. In this case, it's a surface load. What happens then is that a submodel is created in the background of RFEM. In this submodel, this load transfer surface is considered with a really high stiffness, and all connected objects, like for example this member, will be modeled as fixed supports instead. So these supports are completely fixed. All 6 degrees of freedom are fixed. Then the submodel will be calculated, and of course you receive your support reactions. And the third step is that these support reactions will be applied on the connected members back in the main model. So to imagine this, I will show you the submodel in some moments. But first, let us finish the creation of the surface. So I apply with pressing OK. And then we have to select our boundary lines so that the surface will be created. So that is done. And now, of course, we also have to apply a load, because without load, we would not see anything. Therefore, I create a new surface load. I want to have a load magnitude of 1 kilonewton per square meter to keep it simple. And the load direction should be in global set on projected area. We can apply this and select the loaded surface, which should be the right load transfer surface of our roof. Okay, now we see the defined surface load, but yeah, basically that's not the visualization or not the load that we want, because we want to transfer this load to the connected members. And to see how this load is transferred, we have to change the visibility a little bit. So we will go to the navigator display, and you will find the setting under model, surfaces. And then you can see there's the option loads from distribution surface. And if we activate this option, then we will already see the distributed or the transferred loads and not the surface load that we can see at the moment. So I will activate it. And okay, we don't see anything. Why is that so? Because the submodel, which I talked about, has not been calculated yet. So to start this process, we have to start a calculation of this load case. And as soon as I start the calculation and the solver starts, you will see that there are two separate calculation processes. And yeah, that's a hint, because the first calculation process is made for the submodel, and after that we do the normal calculation process for our main model. So I hit the calculation button, and as you can see, maybe I can move the window a little bit. Now the mesh is generated for the submodel, and now the calculation, the structural analysis or static analysis, is done for the submodel. If it's finished, we should see loads. That's the case now. And now the mesh is generated for the main model. You see, now the mesh is generated. And now the static analysis is done for the main model. And after that, we will receive our results for the main model. So I think it's clearly visible in the solver that the submodel has to be calculated first, so that we receive these transferred loads. In this case, also my horizontal bracing has received some loads, and probably that's not the thing that I want. But that's not a problem, because we can simply deselect these members to be loaded. For that, we go back to the load transfer settings. And here we can select in the middle part of this dialog which objects should be loaded. By default, all members, all lines, and all nodes which are part of the surface, so these are integrated objects and connected objects, all these are loaded by default. But we can remove the influence of some of these objects. For example, I will choose the members of my horizontal bracing. And by clicking OK, we of course have to calculate again, but then these members won't be loaded anymore. It's also possible to select one member and all members which are located parallel to the selected member. And then you can remove the influence from all these parallel members. Same is for the lines and parallel lines and for the nodes. Okay, let's calculate this again. And yeah, here we see again that it's calculated 2 times. First time for the submodel and second time for this steel hall model. That was the first time, and now the steel hall is calculated. And now it's finished. Okay, so now we received our transferred loads. I can also switch back to the original load, which is the surface load, and switch back to the transferred load. In this case, we only have member loads. The main load is a vertical load as expected, and we have some small effects which result in horizontal loads, but yeah, most likely you don't have to pay any attention to these loads because they are really small, like 0.001 or 0.02. So that is just an effect of the FEM calculation. Okay, I would like to show you the submodel as well. And yeah, I prepared this in a separate model of RFEM6. So I just created the submodel of this one load transfer surface. As you can see, we also have the roof pitch, we have the surface load on the surface. And in this case, the members, as I said, are now modeled as fixed supports. The definition of the surface is a bit special. So it's not a complete rigid surface, but it's a surface with the stiffness type standard and defined stiffness matrix. So let us have a look into the stiffness matrix. And we will see that the different stiffness coefficients are set to a relatively or a really high value, like 1e plus 10 or 5e plus 9, or maybe here also 1e plus 11. So this is a really high stiffness, but it's not a complete rigid surface. It still has an ending stiffness. The reason for that is because this leads to a better result or to a better load distribution. So that's why this load transfer surface is set to this stiffness in the submodel. And if we calculate the system, then we will receive the support reactions of these fixed supports. And this will be exactly the load which is applied in our main model. So for example, we can remember this value here. This is the peak value of the middle rafter. So in this case, we have 1.375 kilonewton per meter. And if we switch back to our main model, we will find exactly this value, which is 1.375 kilonewton per meter. So yeah, with that, I think we have proved that it is the same. Okay, so let's go back to the definition of the load transfer surface. And this time we will have a look at other methods, which is the stripe method. Therefore, I will go to a new load case, which is the second load case. And here I defined a trapezoidal load for the left side of the roof. Let us have a look at the load transfer surface, which I have already defined. So we go back to the tab load transfer. And in this case, we see we have defined X stripes. And this means that the surface, which we see here, is divided into many, many stripes along its local x-axis. So if we strive over with our mouse, we can see, okay, the local x-axis is located in this direction. So it means that the surface will be cut or divided into many stripes, like I am showing with my mouse. So in this way. So you can imagine, like, if there would be many single beams which are lying in this direction on the roof. And every of these beams or every of these stripes is loaded with this trapezoidal load. And always if such a stripe cuts a member, like for example these rafters or also the horizontal bracing, then these members will be loaded by the stripe. So I will go on. No, I will first of all select the loads from distribution surface so that we can see the result of the load transfer. And as we see now, okay, the horizontal bracing is also loaded and our rafters. What is not loaded is the purlin of the rim and of the middle. And the reason for that is because the purlin is completely parallel to the stripes direction, so it does not receive any load. If we change the stripes to Y stripes, then of course the purlin should be loaded and our rafter should not be loaded anymore. So I will change it and apply. And now we see, okay, the purlin is loaded, but rafter is not loaded anymore. So these are the two options that you have to divide the stripes in X or Y direction. And the third possibility would be to mix these two stripe directions. So in this case, you have X and Y stripes. And that's, it's basically like a mix of the two methods. So if we select it, you will see that now all members unimportant of their direction are loaded. Another options that comes with the stripes method is the load distribution. Normally it's set to varying, but it's also possible to set the load distribution to uniform, and in this case you will always receive a constant load distribution on any object. So if I set it to uniform, we will see that this linear load distribution will change to a constant load distribution. In some cases, this can be an advantage to probably keep the system a bit more simple. Maybe also to prove it easier if you calculate it by hand. But of course, the load distribution varying would always be the more exact method. Okay. Next, I would like to talk a bit about the parameters you can see at the right side, or in the middle top side of the dialog. And before we can change or edit something in the parameters, we have to activate the option Advanced Distribution Settings. All these parameters, the stripe width, the smoothing factor, and the minimum number of stripes is only relevant for the stripes method. So for the isotropic method, you don't need any of these parameters. Okay, let me explain what these parameters mean. I already explained how the stripes work, and it's also shown in this little image here on the bottom. So if you see these pointed lines, you can imagine that this is the cut of the stripes. So here you see a visualization of the stripes. And with the first parameter, the stripe width, you can modify the stripe width, which has also a dimensioning in this image. Normally it's set to 10 millimeters, which is a really small value. But if I want, I could also change it to a higher or even to a lower value. For example, I could change the stripe width to a really high value. Maybe we will see something by that. So I changed it to 100 millimeters, press apply. And now we can see that something changed here for the load distribution. Because now we see many steps here, and this is, this comes from the stripes. And it's the same like shown here in this image. The reason for that is that every stripe only calculates a constant load distribution for the connected objects like this member. So the line load or the member load will always be constant for the pure calculation of this load distribution. But of course, this stepped load does not make so much sense, so it's not realistic. And this is the reason why we need the second parameter, which is the smoothing factor. So if you don't wish to have such steps for the visualization or for the load distribution, we can raise the smoothing factor. So the higher the smoothing factor is, the stronger it will get smoothed out. So you also see this in this image. Here we have a smoothing factor of 0.001, which is the smallest possible value. So it means that the loads are not smoothed at all. So that's the pure result of the calculation of the load transfer. And with the value k is equal to 1, we have a really smoothed out result. So in this example, I could raise the smoothing factor, for example, to 0.5, which is already a relatively high value, and apply. And as you can see, now we also have a smoothed load. Okay, let's change it back to the minimum value. So we want to see the unsmoothed results again. And let me increase the stripe width to a really high value, which, for example, 1000 millimeters, which is 1 meter. So normally we should receive only 2 stripes now, because the roof has a width of 2 meters for this one side. Now I apply, but we see, no, that's not the case. We still have many small stripes and not the 2 expected stripes. The reason for that is because we set the minimum number of stripes to 20. So that's the rule. Unimportant of how big I choose the stripe width, it should always be at least 20 minimum stripes. This means that if I would count the steps here, I would receive the number 20. So that's exactly 20 stripes at the moment. If we lower the value to like 5, for example, then we will see, okay, now we only have 5 stripes. Yeah, with these parameters, you can play around a little bit and change how the stripes are considered. It's also possible to to set a surface weight if you want. That's just an easy way to consider the weight of the surface, but it's the same like if you would apply the load by hand outside of the load transfer surface. Okay, this would be the settings for the parameters, but we still have some more options on the bottom of the load transfer dialog. At the one hand side, there is the option consider member eccentricity, and the next option is consider section distribution. This means that if we define an eccentricity or a section distribution for our members, then this will be considered for the calculation of the load transferring. So normally it's not considered. This means I can apply any eccentricity, but the transferred loads will always stay the same. With these options activated, the eccentricity would change how the loads are transferred. So yeah, basically, if we activate the considering of the member eccentricity, then the real location of the member with considering the eccentricity would be set. The section distribution means how I will show you the setting. So you will find it in the edit member dialog in the tab sections, and here you see the section distribution. So normally it does not have any influence, but if you have like tapered members, then this option is relevant. So normally, if you don't consider the section distribution, the member location is considered like in this line here. If you enable the option, then for the tapered ends, the middle of the cross-section height would be applied. So in this case, the axis would be would have a little pitch. This can lead to small differences between the load transferation, but the difference should not be too big for the most cases. Okay, and one last option is the option neglect equilibrium of moments. By default, the setting is deactivated, which means that the equilibrium of moments is considered. And I can show you that in my third prepared load case. And here I defined some local loads on our load transfer surface. I have two nodal loads. I also have a free line load and a free rectangular load. This could probably happen if we have some, for example, air conditioning on the roof, or if there are some pipes which are connected with the roofs. So this could be cases where we have such types of loads on our roof. And of course, it's also possible to transfer these loads which are applied on the surface to the connected objects like these members. Normally, the equilibrium is considered. This means, for example, for this load, it's located in 2/3 of the span of this roof. So it would mean that 2/3 of the load would go to the right rafter, and 1/3 of the load would go to the left rafter. This is the case, as you can see it. Here we have one moment. I still want to change something. I will change it back to X stripe so we can see it a little bit clearer. And as I already explained, 2/3, which is the value 0.667, go to the right rafter, and 1/3 of the load, which is 0.333, goes to the left rafter. And equilibrium of moments is considered for the distributed or for the transferred loads. Same is for all other types of loads. But now, if I activate the option neglect equilibrium, then the equilibrium does not matter anymore, so it's not neglected. So what does it mean in detail? It means that now you can imagine like there's a cut done in the middle of this span between the left and the right rafter. And every load that is located on the left side of this cut will be transferred to the left rafter. And all load that is located on the right side of the span will be transferred to the right member. This would mean, for example, that this free rectangular load, which is completely located on the right side of the span, will be completely transferred to the right member. So that's different to the case before. If I activate the load from distribution surface, we will see this. So now we have one, so the complete load on the right rafter of this rectangular free load. And on the left side, we don't have any load in this case. If the load is located completely in the middle, then it will still be like before. So we have half on the right and half on the left. And there's also one special case, because for these loads, which are nodal loads, the equilibrium is always considered correctly, also if the option is activated. So also for this load, which has eccentricity to the middle of the span, the loads are still distributed 2/3 and 1/3. But for all other loads, the equilibrium won't be considered anymore in this case. Okay. I just remembered one thing that I would like to show you again. And by now, we always only transferred the surface load on this load transfer surface to members, which are connected to the surface. But I would like to show you that it's also possible to transfer it to lines or to nodes. So like shown here. Now it's not transferred to these objects. The reason for that is because these nodes and this line are no structural objects. It's just geometry, and it does not have any stiffness or something like this. So that's the reason why the loads are not transferred. But if I, for example, put such a nodal support on this node, then it will instantly also receive a load. Same is for the line. I could put a line support there. And then we will see, okay, now also the line has some loads transferred to it. Of course, that's also possible, for example, if you have a wall which is connected to the load transfer surfaces in this line, then also the wall will be loaded. And same for the nodes. If we put a column on this node, let me do it really quick, then also this column, of course, has a stiffness and will be loaded. One thing you have to keep in mind is that only the load of this stripe, which the node or which the line is directed in, will be transferred to the column. This means if you select the stripes method in this case, it really depends on the stripe width. Now we have a very big stripe width. We only have 5 stripes. So the column is getting a relatively high load. But in the normal default setting, let me change it back to the default setting. So we only have a stripe width of 10 millimeters. And this means that the column will only receive a really small load. If I press apply, you see now it's only 0.02. And yeah, for example, if I double up the stripe width, we will receive the doubled loading, which is 0.04 now. So that just means that the stripe width has a big influence to the loads on columns in this case. This is why I would recommend to use the isotropic method if you have some structure like this. Okay, let us remove the column and the line support, because in this case it would not make much sense to have a column here. And now we are back to the default system. One last thing that I would like to show is that load transfer surfaces can also be used for other geometry types. So you don't necessarily need a plane surface. You can also use curved surfaces like quadrangle. Load transfer works the same, and it's still possible. And I think that's a really heavy feature and a big advantage. And the other thing is, that's basically the last thing I want to explain for the load transfer surface. This is the load distribution factor. That's an additional option for the load transfer surface. And if you activate it, you can define load distribution factors if you want. So by changing the factor for some members, for example, I can say, okay, this member should receive a higher distribution factor. And I can say, okay, maybe we choose 1.3 or something like this. Then we will see that the transferred load will increase. So I have to apply it, of course. And now you see the load has gotten bigger. Be careful a little bit with this function, because if you increase or decrease the distribution factor, you will also increase or decrease the sum of the loads. So you will receive a higher surface load or a higher load at all. This means that you increase the absolute values of this load, and it's not relative to the sum of the loads. Okay, but it's, in my opinion, also a really useful feature if you want to, kind of manually have an influence to the load transferring. Okay, that's already everything I wanted to explain for the load transfer surface. And as I said at the beginning, we also have two other points that we want to have a look at it today. And this is the two load wizards, member loads from area load and member loads from free line loads. To show that, I will switch to the load case 4 that I already have prepared. I want to use just this load case to show you the first load wizard, member loads from area load. For example, we could imagine that we want to apply member loads from an area load, which is the result of a wind load on our steel hall wall. Therefore, we can create a new load wizard. We can do this by double-clicking here or by right-clicking and selecting the option New Load Wizard. Now we see the dialog for the definition of the member loads from area load. This load wizard has an advantage, and the advantage is that we don't have to manually define our surface like we had to do this for the load transfer surface. So we don't need any surfaces at all. That's especially an advantage if you are working with R-Stab, because there you don't have any surfaces available, and you can still use the load wizard member loads from area load. The disadvantage of this load wizard is that you can only apply surface loads. For the load transfer surface, you have seen that we can also apply, for example, nodal loads and free loads. So we can apply every type of load to the surface. For the load wizard, only surface loads. Okay, let us generate our load. We want to generate it in load case 4, and we want to choose the uniform load distribution in global X direction. So I choose global X. And the load magnitude should still be 1 kilonewton per square meter to keep it simple. And there's one thing we have to define to finish the input for this load wizard, and this would be the geometry of our surface load. Therefore, we can pick our corner nodes for the area or for the surface we want to apply the load on. And I think the easiest way would be to pick the nodes in the main model. So I select the corner nodes here of our wall of the steel hull. And now we are ready to go and can press OK. And that is the result. Normally, or by default, we still see our defined surface or area load. But again, it would be interesting to see the transferred member loads, because these are the real loads that are considered for the static analysis. To achieve this, we go back to the navigator display, scroll down a little bit to where is it? To load wizards, and then member loads from area load. And here we can choose the option display separately. And now we see the load distribution on the members. Alternatively, you can also select the load wizard load, right click and choose display separately. It's basically the same. Okay, now we see the loads, and maybe you could wonder, okay, why is there such a corner here, and here's also a little corner on this load. I cannot explain why this is happening. And in this case, it's really useful to have a look at the distribution areas of the of this load wizard. And this is possible to show in RFEM 6, and I think it's a really powerful or really cool feature. And to achieve this, we have to go to the navigator display and select the option display distribution areas. So I enable this, and yeah, I still don't see anything because I first have to select the load wizard that I want to show the load distribution areas. So now I select it, and we get a really nice overview of the distribution areas. And by seeing that, it will be a little bit clearer why we have these peaks or these corners here in the load. Yeah, now it makes much more sense, and it's a good visualization option in my opinion. Okay, let us go back to the definition of this load wizard, and we want to have a look at the additional options. These two options will be familiar to you because it's the same like for the load transfer surface. Also here you can consider the member eccentricity and the section distribution if you want. So it's completely similar to or identical to the load transfer surface. Then we also have this first option, which means lock for new members. By default, it's deactivated. That means if I would create a new member now, like an additional column, then this would be synchronized with the load wizard, and also this additional column would be loaded, or the loads would be transferred to this column or to any new member. If we check this box, then we can lock this state we see here, and I can add any new members in this plane and they won't be loaded. The smooth concentrated loads option, I will show this in some minutes, but first of all, we will switch over to the geometry tab. And here we have also the option to remove the influence for some members. It's also basically the same like for the load transfer surface. So for example, if I want to remove the influence for the horizontal bracing, then I can do it with the selection. I can apply it, and then we see, okay, now the horizontal bracing is not loaded anymore. but yeah, the other members receive a slightly bigger load instead. Then there's also a really powerful setting, in my opinion, or yeah, I think that's a really cool setting and you can do many things with it. And this is the area of load application. By default, we apply the load on a fully closed plane. This means that this complete plane has an area load, which has to be applied on the members. The second option would be to only have an empty plane and the load only on the members. So let me choose this option and apply it. First of all, we see, okay, the loads are getting much smaller, and that's because now only the surface where we have our members is loaded. For example, you can imagine that this hall is open, so it has not a wall, only the columns, and we have a wind load. So the wind can flow through the hall, and it only creates wind pressure on the members. So this would normally be the use case for this option. And what is really cool about it is that the exact surface of the section is considered. This means that the columns with the bigger cross-section also receive a bigger load than the columns with than the purlins with a smaller cross-section. And what is also considered is the rotation of the member. So if I, for example, define a rotation of 45 degrees, then we will have a bigger load distribution for area for wind loads, for example. And as you can see, the load will increase to 0.17 kilonewton per meter. And with the unrotated member, it's only 0.12. So that's a really powerful tool, in my opinion. And yeah, especially for wind loads, this can be really helpful, for example, for truss systems and so on. Okay, to show the other functions for the load wizard member loads from area load, I would like to create one more load wizard. So basically, it's possible to create as many load wizards as you want in the same model. It's not limited to one. So yeah, I will create a new one. And this time I want to have global load direction in ZP direction with 1 kilonewton per square meter. And I will pick a geometry which is a bit different or a bit special. So I pick, first of all, the corner nodes of our left side of the roof. But here I will do it a little bit special. So I pick this middle node of the surface and then I complete the surface. So now we see that this area does not receive any loads. And yeah, we also see that the purlin, which is outside of the load distribution area, does not receive any loads. This means that only members in this plane and it's like I said, only members in this plane are loaded. But we can modify this a little bit by modifying our tolerances. So for example, I could say, okay, I want a tolerance of delta S of like a really big one, like 0.5 meters. This is already a really high tolerance. But this would mean that also members which are located 0.5 meters outside of the plane will be considered as well. So let us apply it. And now we perfectly see again on this load distribution area that we have such a radius of 0.5 meters outside of our predefined plane. So this means that every member which is located in this tolerance area will also be considered for load distribution. So in this case, this purlin again is located inside of the tolerance area, which means it receives loads. If I lower the tolerance a little bit, for example, to 0.3 or maybe to 0.4, then we can see that a small part of this member is outside of the tolerance area or of the load distribution plane. And we see that this part of the member is not loaded anymore. In this case, we have such a bit strange nodal loads on the member. This is caused because we have kind of a concentrated load in this location. If you don't want to have these nodal loads, you can activate the option smooth concentrated load. So that's exactly for this case. If you receive some loads like this, you can, if you want, smooth them, and then the loads will be considered within the member load. So the member load will increase a little bit, but the nodal loads will be removed. So it's up on your turn. You can do it if you want. Probably it will be a bit of an advantage for your system. You can decide if you want to apply it like this, or if you want to consider this as nodal loads like it's done by default. I only talked about the second tolerance option, but there's also this first one, and this is for members which are out of the plane. So for example, if I would have a member which is a bit delayed in the global Z direction, so it's a little bit higher or a little bit lower, so it's not directly in the plane that I have defined, then we can change this tolerance to a higher value to also consider these members outside of the plane. So these are basically the two tolerance options that we have available. I think that would already be everything for the member loads from area load wizard. And so we can go to the last one, which is the member loads from free line load wizard. Let us create a new line load. And as you can see, it's relatively similar to the first load wizard. The difference here is that we don't apply a surface load, but we apply a line load, as you can see on this small little image. For that, we again have to say, okay, we want to define it in load case 5. We want a uniform load distribution in global Z direction. Of course, we also have defined the load magnitude, and now we need to define the start and the end node of this line load. I think the easiest way to do this is by picking it in the model. Best way to do this is by pressing this button, because then you can select both nodes with at the same time. So I picked the first and the last node. You could imagine, like, maybe if there is a pipe or something on the roof, or technical equipment, then this could be the use case for such member loads from free line load wizard, because it's, if you have, for example, a pipe which goes from start to end of this hall, then it has a constant load over its length. But yeah, it will be connected only with the members probably and not with the surface. So this would be the perfect use case for this load wizard. Yeah, I think I don't have to explain too much about the options because it's exactly the same like for the load wizard before. We can also lock this for new members so that they won't be loaded. And we can also consider the member eccentricity and the section distribution if we want. Let's apply it. And also here we can say, okay, display separately. And then we see all our punctual member loads that have been transferred to the members. Basically all members that are cut by this line are considered for load distribution. But also here you can define tolerances. In this for this load wizard, only the second tolerance is relevant. So the first one does not have any impact. But if you want to add a small tolerance, you can do it by changing this value. And this would mean that also members which are not directly cut or cut by this imagined line can also be considered. And as you are probably already used to it, you can also select that some members should not be loaded. So we can, for example, say, like always, we don't want to load our horizontal bracing and apply this. So now the loads are only applied on the rafters. Okay, so that should be it for all three possibilities of load transfer. And one last thing that I would like to talk about with you is the small outlook for planned features in the future. For that, I will switch back to the PowerPoint presentation and go to the next page. And it's not that much, which has to do with the load transferation, but there are two things that I would like to tell you that we are planning at the moment. And the first one is the option of hierarchy levels. And part-wise, this is already included in RFEM 6 in the actual state, for example, for the building model. So on the right side, you can see this image. This is a typical building model. So we have walls, we have ceilings, and we also have columns. And the problem or the task is that we have horizontal loads on the walls, and these loads have to be transferred first of all to the walls, from the walls to the ceiling, and from the ceiling to the columns. So these are multiple steps for load transferation, and for that we need something like hierarchy levels, so that we can define a priority which load transfer surface should be considered first and which one should be considered next. For the building model, it's kind of clear how this has to be done. So in this case, the walls have hierarchy 0, so load is distributed on the walls. We calculate the support reactions of the walls and apply it as external loads on the ceiling. Then these external loads of the ceiling are transferred back to the columns. So that's the way how it works in the building model. But this could probably also be a useful feature in general, not only in the building model add-on. So probably we will receive it as a feature in the future. So you could have something like a construct of multiple load transfer surface and define the hierarchy, which load transfer surface should transfer the loads to the next connected load transfer surface. So something like this could happen in the future. And the second feature that I wanted to talk about is a new member type, which would be the load transfer member. Yeah, you probably can imagine what is meant with that. It's basically the same like the load transfer surface, but just as a member type. So we have a 1D object which can transfer loads. So the principle would be the same. We have a member which can, where you can apply loads on, and these loads are transferred to connected objects. But the member itself does not have any stiffness for the system, so you don't stiffen your system with these load transfer members. That's the basic idea, and this is, at the moment a planned feature. Okay, with that, this was everything from my side. I hope you could learn something new for this big topic of load transfer. And I also hope that you are now able to use it by yourself and have an advantage of this feature for your own projects. Okay, now I have said everything from my side, and I would give back the speech to my colleague Andreas.
Thank you, Niklas, for your presentation. I have an additional hint. You can book our online courses, for example, the RFEM 6 masterclass course. That course is for beginners. Then we provide also an Eurocode 2 and Eurocode 3 course. To get more information, just scan the QR codes, or you can click on the buttons at the bottom. Then you get also the prices and so on. Okay, that's also all from my side. I thank you for your attention. Thanks to Niklas for the presentation. I wish you all a nice rest of the day. Bye-bye.